Hello everyone, myself Harshit Pratap Singh and today we will be discussing about IO devices and its subsystem. Today we will be discussing about the overview of IO management system, IO hardware, a typical PC bus, types of IO devices, characteristics of IO devices, device communication, polling, interrupts, DMA, and kernel IO subsystem, life cycle of an IO request, performance, its measures and role, and some important terms. First, we see the overview of an IO management. IO management. IO management is a major component of an operating system. Operating system design and operation. Design and operation. It is an important aspect of computer operation as giving input and taking output from an PC is very important for the user and the client. IO devices vary very greatly. Various methods to control them, as we can control IO devices by using buttons, mouses, and touches. New types of devices are very frequently introduced, like SCSI devices, keyboard, mouse, PCI bus, floppy disk drives, ATI. All are these IO devices because we take input or give output from these or to these devices. IO hardware. Hardware is generally connected through ports, buses, and it has device controllers to connect to various devices. Device drivers encapsulate various device details, like how the device will interface to the IO subsystem, how it will take input from systems, and what the codes will mean to each other. We have an incredible variety of IO devices like storage devices, transmission, human interface devices like touching digitizers, very common concepts. Signals from IO devices interface with computer. We have ports for the connection point for devices. We have bus daisy chain. We have two types of buses, daisy chain or shared direct access. PCI buses are very common in PCs, servers, and PCI expresses. Peripheral communication interface. Actually, the PCI is commonly an abbreviation for peripheral communication interface bus that connects the devices of PCs to each other. Expansion bus connects relatively slow devices. We can also easily expand the storage connection. So controller or host adapters are the devices that operate over port, bus and devices. Sometimes they are integrated or sometimes they are separate from circuit boards or host adapters. They contain processors, micro code, private memory, bus controllers, and etc. Some talk to pure device controller with bus controllers, microcode or memory, etc. IO instructions control devices. There are many instructions that control different types of devices, like in controls the input devices, and out instructions are used for giving output to a device like monitor. Devices usually have registers where device driver places commands, addresses, and data to write or read data from registers after command execution. Data in register or data out register, status register, and control registers are different types of registers that are generally present on the devices. Typically, they are 1 to 4 bytes of FIFO buffers that are generally used to store data in a sequential manner. So here is a Typical PC bus structure. Here we have ID, disk controllers, output device, processor, PCI bus, peripheral control interface bus to interfacing various devices to each other. We have SCSI controller, small control system interface bus, keyboard input device, serial ports, parallel ports, expansion bus to connect various other devices, expansion bus interface to interface the expansion bus with the PCI bus. As in PCI bus we have very few ports due to its high speed, and to increase the performance of PCI bus we can't connect many ports to each other, so we use expansion bus to connect more devices. We have IDE disk controllers for controlling various other disk drives like floppy drives, DVDs, CDs and hard disks. Types of IO devices. We have mainly two types of IO devices on the basis of the date transfer. First, we have block devices. In this type of device, we commonly transfer a block of data from a single device to another device. Like we have commands include read, write, and seek. We have raw input of file system access, and memory mapped file access is also possible with the block devices. For character devices, and second we have character devices which includes keyboards, mice, serial ports. In this we have commands like get or put. Get is generally used to take input and put is used to give the output or pass the output to an output device. Libraries are layered on top, allow line editing. Here in the diagram we can see we have CPU. The data comes in a serial manner and it passed to memory, and then it's passed to the output devices like monitor, printer, speaker and other outputs. Block devices are mainly, or we can say, are storage devices, as we can access random bits more easily in these. And character device mainly pass serial commands or serial instructions to the PC. Characteristics of an IO device. First we will characteristics of an IO devices. Data transfer mode. What is the transfer mode of the data device? In this we have two variations. Character, we can pass characters or a block of characters. For example, we have terminal. Terminal screens are used for generally passing a single command or a few commands at a time. And in disk, we can pass a block of input output easily. What is the access method of a device? It can be sequential or random. For example, in sequential, we have modem, and random can be defined as random. For the random example, we have CD-ROM. Transfer schedule. What is the scheduling method we used? Synchronous method or asynchronous method? For synchronous, we have tape, and for asynchronous, we have keyboard example. What is the sharing method? Dedicated or shareable? In dedicated, we have a purpose that for a device that it will serve only a specific user or a specific device. Or in shareable type we can share a single device with few users or few devices easily. For example, a tape drive and keyboard. Device speed. What is the speed of the device? Its latency. Seek time. What is the seek time of a device? What is the transfer rate? Delay between operations of few serial instructions or commands. What is the IO direction? Is the device read only or write only, or it is read write both? at the same time. Like CD-ROMs are read-only devices, graphics controllers are write-only devices, and in disk we have both read and write instructions. Communication between devices. The device manager relies on several auxiliary features to keep running efficiently. The devices mainly communicate using device managers. There are three problems that must be solved. It needs to know which components are busy and which are free, which are it must be able to accommodate the requests that come in during heavy IO traffics, and it must accommodate the disparity of speeds between CPU and IO devices. We can say a device manager is like a middleman that works in between CPU and IO devices. The first is solved by structuring the interaction between units. We can solve our first problem by using different structuring for interaction between units. And the last one can be solved by buffering records and queuing requests. The success of operation depends on the system's ability to know when a device has completed an operation. These three problems are very important for a device and device manager to work perfectly or more error free. Device communication continues. This is done by hardware flagging. We can easily flag for different conditions and check for them by the CPU. The flag is made up of 3 bits and resides in the channel status word or CSW. Generally, it is a predefined location in the memory that contains the information indicating the status of the channel. Each byte represents one of the component of the IO system. In first part, we have the one for channel and one for control unit and one for device. Each bit is changed from 0 to 1 to indicate the unit has changed from free to busy. 0 means free and 1 means busy. Each component has access to the flag. The flag is tested before proceeding with the next IO operation to ensure that the entire path is free and we can proceed with no errors or no overwriting. There are two common ways to perform this test: polling and interrupts. We generally poll for a test and or interrupts to apply this. Polling. In polling method, we determine the state of device. Is it command ready, busy, or error? For example, the CPU periodically tests the channel status bit in CSW. If the channel is busy, the CPU performs some other tasks, else the channel performs the IO operation. Busy waits cycle to wait for IO from device. If the channel is doing some work, then we will wait for the cycle to complete for the IO from device. Inefficient when attempted. The polling is very inefficient if we repeatedly check for different conditions, yet rarely finds a device ready for service while other CPU processing remains undone. More efficient for the hardware controller to notify the CPU when it is ready for service rather than to require the CPU to poll readily for an IO completion. Second type, interrupts. It is a more efficient way to test a flag than polling. In this, a hardware mechanism does the test as part of every machine instruction executed by CPU. In this, the device automatically sends a signal to CPU that it needs to do some IO operation. If the channel is busy, the flag is set so that execution of the instructions is automatically interrupted. Control is passed to the interrupt handler, part of the OS which resides in a predefined location of the memory. Find out which unit sent the signal. It then analyzes its status and restarts is where appropriate with the next operation. Then it returns the control to the interrupted process. Some systems have hardware that can distinguish between several types of interrupts. These interrupts are ordered by priority. Each one can transfer control to a corresponding memory location, and hardware will intercept all interrupts of similar or lower priority. So, what is the cycle of an interrupt driven IO cycle? First, the CPU will the device will initiate an IO device. Then we will tell the CPU, and after that it initiates an IO. Then we check, is the device input ready, output complete, or error generates the input signal. Then the CPU receiving the interrupt transfers the control to interrupt handler. Then the interrupt handler processes the data and returns from the interrupt. In this phase, the IO device will complete its processing and the data transfer will be completed. And after this, the CPU will resume the processing of interrupted tasks in the first step here. Interrupt mechanism are also used for exceptions. Exceptions are errors that are caused during the runtime of an process. In this, the we terminate the process and crash system due to hardware failure. Page fault executes when memory access error. System call executes via trap to trigger kernel to execute request. Multi-CPU systems can process interrupts concurrently. If the operating system designed to handle it, we use time-sensitive processing. Frequent must be fast. For example, we can see in mainline code we have loop function in which instruction 1, 2, 3, and 4 and 5. But between 2 and 3 we have an interrupt or interrupt service that must be served. When the CPU encounters after the second instruction line, we go to an ISR function and it is executed. Instruction 1, 2, and 3 of the ISR will be executed, and after its execution, the control will return to the mainline code, after which the mainline code was interrupted. In this example, it is instruction 3, and the whole process will be go on easily and as it was coded. The third and the last method, direct memory access or DMA. We have we use this method to avoid programmed IO, or we can say one byte data transfer at a time. This is generally used for large data transfer movement. In this, the CPU will be the control of the data bus will be handled to the DMA or DMA controller. The CPU is bypassed to transfer data directly between IO device and memory. The OS writes DMA command block into memory. Source and destination addresses are written on the stack. The read and write modes are selected, and we count the bytes. We write the location of command block to DMA controller, and bus master of DMA controller grabs bus from the CPU. Cycle stealing method of a DMA is much more efficient as the CPU will also continue its working and the data transfer will also be executed. The data transfer will always take place in between the execution of free cycles of the CPU. When the data transfer is done, the interrupts to signal completion. We send an interrupt signal that shows that we have completed the data transfer, and the data bus is returned. The control of the data bus is returned to the DMA, to the CPU automatically. The version that is aware of virtual addresses can be even more efficient, or we can say DVMA, data version memory access. Kernel IO subsystem. A kernel is a very core component of an OS that generally manages the IO device, hardware devices, and softwares, or we can say it manages the resources uh, and their power supplies and different instructions. Scheduling. Some IO requests ordering via per device queue, and some OSs strive fairness, while some implement quality of service IPQoS. We sometimes use buffering to store data in memory while transferring between devices to cope with device speed mismatch. Generally, the device accessing speeds are very different for CPU, as it is placed very far from the CPU. To maintain copy semantics, double buffering two copies of the data. We have one for kernel and one for user. They have varying sizes and full of being processed and not fully being processed. Copy on write can be used for efficiency in some cases. Caching. Faster device holding copy of devices. Cache is a small space of memory that is generally placed very near to the CPU, and it is very fast to access. It always contains a copy of the data. We generally use cache to match the performance of CPU to other devices. Sometimes it is combined with buffering. Spooling, hold output of a device. Spooling is a method in which we hold the output for a device. If the device can serve only one request at a time, for example, printing, many jobs are sent to printer, but only one request will be processed or served at a time. So in this we use spooling. Or device reservation provides exclusive access to a device. System calls for allocation and deallocation. We generally watch out for deadlocks as they are very common in device reservation. Life cycle of an IO request. First, we request an IO through a system call. Then a condition will be checked that the request is already satisfied or not. If it is satisfied, then we transfer the data or error code. IO completed or output completed. If the satisfy request is no, then some request to device driver and block process if appropriate. If the priority of the IO device is very high, then we stop the current processing process and pass the control to the device. Process request issue commands to controller and configures controller to block until interrupted. Device Then it is sent to interrupt handler. Device controller commands. We monitor device for interrupts when IO is completed. If the IO is completed, an interrupt is generated that tells the interrupt handler to store the data in device driver buffer if the input and signal to unblock the device driver. Then the device driver determines which IO completed or indicate the state change to IO system. Then we transfer the data to the process and return completion or error code for that. Then IO completed, data transfer is available. This is the whole life cycle of an IO request. Performance. What is the role of an performance in IO device? IO is a major factor in system performance, as if the IO devices are very slow in comparison to the CPU, then it will demand CPU to execute device driver, kernel IO for context switching will be a more context switching will be a heck for that due to interrupts. Data copying will be interrupted. Network traffic especially stressful become stressful. Solutions for these solutions for these performance issues. We can reduce the number of context switches during IO processes. We can reduce data copying. We can also reduce interrupts by using large interrupts. We can also use DMA for transferring large blocks of data. We can use smarter hardware devices. We can balance CPU, memory, bus, and IO performance for highest throughput. Move user mode process or daemons to kernel threads. We can reduce the interrupts by using large transfers, smart controllers, and polling methods. Last and the final point. Some important terms. Blocking. A blocking is a process in which an process in which a process will be suspended until an IO is completed. Blocking is very easy to use and understand. It is insufficient for some needs. Non-blocking devices. IO calls return as much as available. User interface data copy. We have buffered IOs it is implemented via multi-threading. It returns quickly with count of bytes read or written. Select method to if it is it has a select method to find if the data is ready, then read and write to transfer data. Asynchronous devices. The process runs while the IO executes. In this, we parallelly run a process and IO is also executed. It is very difficult to use. The IO subsystem signals process when IO is completed. Vectored IO allows one system call to perform multiple operations. And this is the final slide. Thank you for seeing or attending this slide.